Hello everyone, welcome to another interesting lecture of control systems. In today's class, we are going to talk about Routh stability criterion. So in our previous lectures, we have seen there are two ways to analyze the control system stability. The first one of which is using the pole analysis, and the second criterion was the Hurwitz matrix arrangement. So today we are going to see another method for analyzing the stability of your control system, which is known as a Routh stability criterion. So in this criterion, so given a characteristic polynomial of a system, we are going to decompose that characteristic polynomial or the equation into Routh array, and then we are going to solve it using the steps that will be shown here. So what basically the Routh array is all about is it takes the characteristic equation and decomposes it into different rows, which maps to the order of the polynomial. So in this case, if you take the first row, that is s to the power of 4, the second row is s to the power of 3, and etc. up to s to the power of 0. And these maps to the, if you look at the characteristic polynomial, your highest power is s to the power of 4. So it starts from that highest order or the highest power of s, and then it goes in descending order till the lowest power of s, which is s to the power of 0. Now if you see, the Routh array composes of numerical values, and the first two rows in your Routh array is obtained from the characteristic equation. So in this case, the 3, 5, 2 and 10, 5, 0, they represent the coefficients of your even and odd power from the characteristic equation. Okay? So the even power comes first because the highest power is 4, which is even. And if you have a question where the highest power is odd, the odd powers come as the first row and the even powers come in the second row. Okay? So the starting position depends on the question and the highest power of the characteristic polynomial given in your question. So if the highest power is odd, your odd coefficients comes first, and if they are even, the even power coefficients come first. The rest of the rows, in this case s square, s1 and s to the power of 0, these rows needs to be computed by us using certain rule sets that we'll be discussing here in this slide. So I am writing again the Routh array with I'm putting all the already computed or known values from the characteristic equations, which are 3, 5, 2 and my 10, 5 zeros. Alright. And now I'm going to find the other rows s square, s1 and s to the power 0. So the row s square is obtained by taking the two rows s4 and s3. So the first two rows gives the third row, and my s cube and s square rows are used in computing the s to the power 1 row. So before we go to computing the s square row, what you need to know is you need to look for common multiples. You need to see whether these rows can be simplified before we start our computation of new elements. So in this case, I have the second row elements to be 10 and 5, and these can be simplified because I have a common multiple of 2 which can be taken out, and I can simplify my s cube row to just 2 and 1. So before it was 10, 5, and now after simplifying it, it is now just 2 and 1. Now I am using the s4 row and my s3 row, and I get my s2 row. Good. So my s2 row is computed, so it is color coded for your understanding. So I am taking my 2 from the s cube into 5 from my s4. So it's a cross multiplication, right? 2 into 5 minus 1 into 3 upon 2, and that is my first value. For my second value is 2 into 2 minus 0 into 3 upon again 2. So this is my s square. And similarly, I can write the next row, which is my s1, s to the power 1, from these two. So 3.5 into 2, right? So the 3.5 into 2. So how it comes? 3.5 into what? Can you tell me? 3.5 into 1 minus 2 into 2 upon 3.5. So for my computation of s to the power of 1, I am using the s cube and s square rows. Then I get the values. Good. So this is how we compute. So this is a very simple numerical, and this is how you compute. So just now see this direction of this arrows indicating how we compute these elements. So the blue arrows indicate how I did my first element in my s square row, that is 2 into 5 minus 1 into 3 upon 2. The second element I am computed for 2 into 2 minus 0 into 3 upon 2. So what I'm talking about is the anchor is the denominator. You see the denominator in both the cases is 2. So that is what I'm calling as the anchor, and that is the first element in your S cube. Right. So for S square, see the computation is going to be that first element 3.5 into 1 minus 2 into 2 upon 3.5. So the anchor is your 3.5. So that is what we call as the anchor element or the anchor. So if you see for all these values that we are computing, right, throughout all the values other than the first two rows, which are obtained directly from the characteristic polynomial, you can easily tell that these things are what you call your anchor points are always the first element. Okay, good. So now that is good for this. I'm filling up with these values that we have computed. Now if you see my s to the power of 1, I am getting a negative value. So that is where I can tell something about this analysis, or that is the stability analysis indicates that if your first column, so the Routh array, after you compute the Routh array to the lowest power, that is s to the power of 0, and then you look at all the elements of the first column, that is what I have shown here. And if you have in these elements, if you have a single, if you have a sign change, you can say if you have a sign change, but if you have a negative element. So it is not, because if you have all positive and all negative, it will be confusing. But I can just say that if you have a negative root, then your system is unstable. So if all the values are positive in your first column, then your system is stable. Yes, your system is stable in that case. And in this case, my s to the power of 1 roots or the terms are negative, which means the system or the characteristic equation given is unstable. Good. So that is how you do Routh array. So what are the steps? The steps are very simple. So given any characteristic polynomial where you cannot factorize it directly, you decompose the characteristic equation into the Routh array. You find all the rows of the Routh array till s to the power 0. Now starting with the highest power of the characteristic polynomial, right? That is the first starting row, and then you go to the lowest power, that is s to the power of 0. You find all the row elements and then see the first column. So the first term in all these rows, if they are all positive, then you have a stable system. That is conclusive for your conclusive that your system is stable. If you find a single sign change, if you have a negative sign in the first column, then your system is not stable. Not just one. You can stop. Whenever you get a single negative term, you can just stop there. You don't have to go any further, because you can just if the question is just a system is stable or not, then you can just tell right there that your system is not stable. Now let's take another question, another example. A little more, what is the difference from the previous question? So this is S5. So the characteristic polynomial is the highest power is 5. So which means it's a fifth order polynomial. And now if you see the Routh array coefficients, they start with the odd power coefficients occupy the first row. The even power coefficients occupy the second row. So S5, S3, S1 occupy the first row, and S to the power 4, 2 and 0 occupy your second row. And then the remaining rows are filled the same way as we had discussed and did in your first numerical. How we did, we are going to do the same procedure here, and the cross multiplication will give you the values. And now there is a special case, because I'm just rather than doing it identical, we will see what are the special cases, or what are the challenges that you can come across. Is what if you get a 0? So here if you see the third row is a 0, right? You get a 0. So when you get 0 on the computation, it becomes very tricky because 0 becomes an anchor point for the next row, and anything divided by 0 is infinity, right? So for your s square term, you will end up getting infinity, and infinity means your system is unstable. So you can directly tell if whenever there is infinity in your system, then that system is not going to be bounded, or that system is not stable. But that is not a very conclusive way to say that your system is unstable because of a division by 0. So what we do is, instead of 0 in that place, I'm going to use something called as epsilon. So the epsilon that you see here is a small value which is close to 0 but not 0. Right, so it can be epsilon can be 0 0.001, 0 0.01, 0 0.1. All these are acceptable values for your epsilon shown there, because that makes sure that your next terms, that is s square row, doesn't go to infinity. Good. Now with that epsilon, I'm computing the s square row in the same way I used to do it. So I have done it. So I get my first term to be 2 epsilon plus 2 upon epsilon, and the second term to be 5. So now let me write all the 4 rows that I have computed so far. And my s square is 2 epsilon plus 2 divided by epsilon and 5. And then s to the power of 1 is, now again I have to compute the same way. So I'm doing it. So now what I'm going to do is, I'm going to compute till my s to the power of 0. This I'm going to do this cross multiplication, and I'm going to find the Routh array, right? I'm going to find all the elements of the Routh array in terms of epsilon. And then after I do that, I just take the first column. So I take only the first column after I do the computation of the Routh array, and then I see whether my epsilon, being a close value to 0, right? Say if I take epsilon to be 0.1, a positive value of 0.1, whether I am going to get all the column values, all the first column values to be positive. If I am getting all first values to be positive, then I can say for sure that my system is a stable system. Now that was my S1, right? So we have computed. Now we will do the last row. So we have done all from S5 to S1, and I have all the coefficients right here. So I'm going to write all the coefficients, and then once I do my S0, that is the last row, I am done with this Routh array. So I can say that Routh array is complete to the last power, or to the last row, which is your S0. And in this case, I can pretty much, if there is no element there, we are supposed to assume that to be 0. So if I multiply this and this divided by the anchor, so I'm just going to get it as plus 5, right? So that should be plus 5. I think I don't know why I wrote it as minus 5. The s square row is having plus 5. So I think I'll change it here. So that big fractional polynomial is going to cancel the numerator and the denominator, because it's present there. And now I think at some place I'll be definitely changing. I'll be writing it as plus 5 surely, because there's a mistake. See, yeah. So that is plus 5. So I've just written it wrongly in that slide. So it is to be taken as plus 5, because your s cube and s4, if you see the elements, so I'm writing everything, and the CUS square is plus 5. So there is no minus 5, it is a plus 5 only. So my S0 is plus 5. Good. So now I computed to the last row, and now I will take my first column and do the Routh array stability analysis. So what do? Is I take this Routh array stability analysis, means I take this first column and see whether these elements are positive. So my epsilon is close to approximately equal to 0, so it is positive. So I'm going to take that as to be 0.1, and let us take about the second. There is 2 epsilon. So for this I'm assuming 0.1, and then that is again positive, right? I could assume, you may ask why not minus point when that is close to 0 on the other side, right, on the negative side. But our goal is not to make the system unstable, right? So if I'm putting it as minus 0.1, then I myself am calling this system to be unstable, which is not what we want. So we keep it as positive and still see whether we are getting. See here for the S1, when I put even point plus 0.1, I'm getting that to be negative. You can easily tell that all are negative signs, so which means that is definitely going to be a negative, and that makes your system here unstable. Good. So we take epsilon to be a positive value close to 0, and then we do the analysis for each terms in the first column and see if they are positive. And if they are positive, then we conclude that the system is stable, and if not, like in the previous question, the system is unstable. And now you have your numerical 3, that is the third numerical, where your power is now s to the power of 6. So the highest power is 6. It is a sixth order characteristic equation or polynomial. And now my first row, the Routh array, will be the even power coefficients, and my second row will be your odd power coefficients. All right, good. So that is done. So always you can write these first two rows from the characteristic polynomial, right, from the question. I can say that for all the Routh array analysis for stability, you can write the first two rows from your question, and the remaining rows need to be computed the same way as I have shown, right? So here what do I do before I do the computation is simplification. So I can see that in my S5 row, I have this 2, 12 and 16, which means I get this 1, 6 and 8. I'm taking the 2 common outside, which means it simplifies to 1, 6 and 8. And now I need to compute my S4 from S6 and S5. So I use this S power 6 and S power 5, and then I compute these values, then I get this one, right? So it becomes 8 minus 6 by 1. So I am just putting color code for your reference, right? So this is the same way how we did, and the anchor point is 1 for the, that is the first term in your S5 row. So the S5 row first term is 1, and that is the anchor point for all the 3 elements in your S4. So your S4 is now 2, 20 minus 8 is 12, and 16 minus 1 is 16. So this is your S4. So now let me write the S5 and S4 here for you. So here again I am getting it as 2, 12, 16, which means there is a 2. I can simplify it. So my S4 becomes 1, 6, 8. Okay, so this is another special case numerical. So we have 2 identical rows. So what happens? So now when I use my S5 and S4 to get your S3, what will happen is I do the element calculation. I find that my S3 rows are going to be 0, all zeros, because my S5 and S4 are identical rows. So when I have identical rows, and now I'm doing all the computation, I can just tell by looking it's going to be all zeros. But for your just to know how do we multiply, how do we calculate this Routh array terms, I'm just going to do it for you. So it's going to be 1 into 6 minus 6 into 1 upon 1. Then it's going to be 1 into 8 minus 8 into 1 upon 1. And then it's going to be 1 into 0 minus 0 into 1 upon 1. So that is going to give all my S cube, right? S3 terms all to be 0. Okay, so this is another special case. So in your previous question, we have seen one case where I have a single element 0 in my row, and when I have a single element as 0, then what do I do is I put that, I make that 0 as epsilon. I make that 0 to be E or epsilon, which is assumed to be a value close to 0. So I don't use that 0 because I get division by 0 and that brings infinity, I don't want to deal with infinity, so I'm just using epsilon. So in this question, I'm getting an entire row to be 0. So I cannot put all values to be epsilon. So when you get an entire row to be 0, what we do is we rely on auxiliary polynomial computation. So what we do now is we go back one row. So S3 is where you're getting all zeros. So you go, you go up. I'm saying go back, but the right thing to say is like go up one row. That is, you take the S4 row and then you obtain the auxiliary polynomial. So if your S4 is an even, right, it's an even order. So your auxiliary polynomial I have written to be S4 plus 6S square plus 8. So the auxiliary polynomial is written with the row coefficients and the powers are determined from that row in which it is located. So in this case, my 1, 6 and 8 are located at S4 row. So my coefficients are written in starting from S to the power 4, as you see there. Now let's take another example. If I have S cube, if I have an S cube row and I want to write an auxiliary polynomial for this S3, right, or S cube, I'm going to write it as S cube plus 2S square. Then I have another one example for S to the power 5, 2, 3, 4. Then my S5 row 2, 3, 4 is 2S5 plus 3S cube plus 4S1. That is the auxiliary polynomial. So this is how the auxiliary polynomial is not fixed. It is not fixed for the Routh array, but instead it is fixed for each row. So which means for S4 you write it in this manner. For S cube it starts with that row. So the highest power is in the row where it is located. So if it is the S power S4 here, the highest power is S4. It's a fourth order polynomial. So that is how you do it. So after you write the auxiliary polynomial, you do the derivative of the auxiliary polynomial. So you take the differentiation of that polynomial, and that is going to give here 4s cube plus 12. And now I'm going to take this 4 and 12 and I'm going to put that in S3. So before my S3 was coming as all 0. So now through my auxiliary polynomial computation, I have taken that S3 to be 4 and 12, and that is okay. It can be simplified further because there is a common 4. So I am doing that simplification. So it's better to do the simplification at all steps possible. If you don't do it also, I don't see, you most of the cases I don't see. There might be some places where it will happen, but I don't know, it cannot be because yeah, so it's better to do the simplification, and then you can proceed with the calculation. As far as this is the rule set which is mentioned in the books, so we are following it. But I mostly when I write programs, I don't go for the simplification. I just keep it as it is and do the Routh array analysis. So I am till now I have not faced any problem by not doing the simplification. So I'm just telling you, in books it's given, so maybe in exams also. So we'll just go by the book, and that is how you get your S square row. And then my final not final, pre-final, right, S1 and I still need my S0. I have to go till S0. So my S1 is computed here. So just keep on computing. So only thing is you get these special case numericals where in this case auxiliary polynomial was to be used, and in the previous case the epsilon notion was to be used, right? These are the special cases. Apart from that, you don't see any other variations or variants in these numericals. You just compute the terms in the Routh array. You just fill the Routh array with these cross multiplications and the anchor divisions. You do that till till the lowest power, just to be sure. As I can tell that here all the terms are positive so far, so which means the system is stable. So I have to keep doing. So my S0 term is also positive. So I can tell now that this is a stable system. So all the terms are positive. So I can call this, this satisfies the stability criterion using the Routh array decomposition. So the Routh array decomposition says that if all the columns, all the elements of the first column are positive, then your system is stable, and that is exactly what we have here. So if I have to summarize, what are the things you have to look out for is these two cases. These are the special cases we get. That is when you have a 0 entry in your column, right? You use, if you have a single 0 in any places, but mostly it comes in your first or second place, then use the epsilon, right? And then the case 2 is when you get all the row element. So when you have two identical rows, that happens when you have two identical rows like S5 and S4 here, then you get the next row to be obviously all zeros. In that case, deploy, what you do is you use the auxiliary polynomial, take the differential of that and then fill that row. Thank you. So that is for today. Thank you.